Hello, it's Keith here, and this is lesson 32 of the platform-specific series of my 6502 assembly programming tutorials. We're back on the Lynx again this week, and we're going to be looking at hardware sprites. Now, fortunately, unlike the sound chip hardware that was very poorly documented, this graphics hardware for the sprites was actually reasonably good, so hopefully I'll be able to get through this lesson without swearing too much. Anyway, you can see here my example before. We've got this bitmap here we drew in the past, and now we've got these two crosshairs, and these are hardware sprites. Now, the Lynx hardware sprites are a little bit different to most systems in that with most hardware sprites, you've actually got a separate layer where the sprite hardware is keeping that image constant, and so the tarmap or whatever else is beneath is changing, but the sprites are still there. The Lynx hardware doesn't work like that. It's actually a drawing engine. There's a hardware processor that draws the sprites into the bitmap memory area. So if we clear the bitmap area, the sprites would disappear. So we have to redraw them every time. But that sprite hardware is very fast. I mean, this is a really powerful system on the Lynx. So the fact that it's semi-software really doesn't matter. Anyway, we're going to look at the special formats that the Lynx uses. We're going to go through the theory of how the sprite format works, and then we're going to look at how to use that to draw the two crosshairs we've seen today. Now, we're going to look at the theory of how to create a sprite in raw byte data, but you don't need to. I've got a program called Sprite Editor, which is free and it's open source, and you can download it as part of the tutorials download. So this is the sample sprite we're looking at today. You can see here the colors are just wrong in this example. But then if you go to 6502 Atari Lynx, you've got all of these options for saving all kinds of bit depths of sprite here. Then that's what we use today. The Atari Lynx can do 16 colors down to 2 colors per sprite, and also there's two kinds. There's a literal sprite, which is an uncompressed sprite, and there's a run length encoded sprite, which is a bit like your GIF. I suppose you could say the literal is a bit like a BMP. The RLE is a bit like a GIF or a PNG. So obviously we want to use the RLE sprites because they're compressed, and as I say, that hardware is so fast you're not going to miss the speed if there is even a difference in speed. So certainly use the RLEs unless you're having trouble with them. Now, that said, we are going to go through the theory of how these formats work. So when we want to define a sprite, we have to pass bitmap data. Now, the bitmap data is basically encoded in a format that the sprite hardware can read indirectly. And so the way it works is it has a few extra bytes that maybe look a little bit odd to a human, but as I say, it's all about getting that hardware to work quickly. So how does it work? Well, first let's have a look at the literal data. This is effectively the bitmap data. And so the first byte in each line is a pointer to the next line of the sprite. So if you imagine this is from left hand side of the screen to the right hand side of the screen, and this is the second line of a sprite, and so this is the offset to the next line. And so there's 1, 2, 3, 4, 5, 6, 7 bytes here, and so 8 bytes long will point us to the next line. And so I think this is so that the hardware can scan down the sprite quickly without having to read all the bytes in between. Now, a literal sprite, if it's 16 color, will be using 4 bits per pixel. So the two nibbles here will be a color. So this would be color 1, this would be color 0, and this would be color 4. Very straightforward format here. So nothing particularly exciting there. But as I say, this is just the most basic sprite format. So this isn't the one I'm really recommending you use. Now, one interesting thing, you'll notice there's a 0 at the end of each line. Now, there's a reason for this. As always with the Lynx hardware, there's bugs in it. It doesn't work properly, but it doesn't work too badly. And so apparently the last bit of each line must be a 0. So just for convenience, I've just made the last byte of each line a 0 because it's far easier than trying to work that out. Color 0 is transparent anyway, so your sprite's a little bit wider than it should be maybe, but it doesn't make any real difference. Now, the last line is a 0 here, and that tells the hardware that it's the end of the sprite. Now, there is another way of doing things which isn't supported by my Sprite Editor, and this is where you split your sprite into 4 quadrants. And so your XY position, instead of being the top left of the drawn sprite, would be the center, and you would draw the top left, the top right, bottom left, and bottom right as 4 quadrants on from that. And if you were going to do that, you would have 4 chunks, and you would have a separator with a 1 here that would define those 4 quadrants. But as I say, that's something fairly advanced, and as I say, I'd really stick away from the bitmaps and just use the RLEs. The RLE format's a little bit more tricky. So the RLE format splits the lines up into individual blocks. Now, the basic line format is the same essentially. You've got the offset to the next line. So if our lines are 8 bytes wide, then we would need the offset of 8. And then what we need next is we need a definition for the type of block. And this is all done in bits, and you're not just splitting a byte up into 8 bits. You could have 3 byte 3 bits of the current byte and then 1 bit of the next byte making up a nibble, for example. And you can see this. I've tried to color this to make things clear here. So these 4 bits in pink are all part of the same command. So the first bit of each block is actually defining what kind of block it is. And if it's a 0, then it's a RLE encoded block. And if it's a 1, then it's a literal block. And the literal blocks, as I say, are just bitmap data. If you're not familiar with RLE, run length encoding, I'll explain it very simply to you here. You basically have 2 parts. You have a count and you have a color. And so if the count is 5 and the color is green, that would mean usually you've got 5 pixels of green. And if you've got 4 and 2, then you've got 4 pixels of color 2. And so this is a simple way of compressing data that has large patches of constant color, which, you know, if you look at my sprite here, for example, if we just zoom it in here, you can see these 4 pixels consecutive are all the same color, and these pixels here are all blank, all the same color. So on a 16 color system, the RLE is going to compress things pretty well. On a 256 color system or a 16.7 million color system, probably not going to work, but for 16 colors or less, really good way of compressing things down. And so that's what we're going to be using in today's example. So here's our block, and it works exactly as described. So 0, this first 0 just is a command saying this is an RLE block. If it was a 1, it would be a literal block. And then you've got a set of bits here, and you can see this nibble is all 1s, which would be 15, but because there would be no sense to a block of 0 pixels, you always add 1. So 0 would mean 1 pixel, and all 1s here would mean 16 pixels. And so this is saying there's 16 pixels of color 0 here, and then there would be more data following on from here. And you can see another example here. You got another RLE block here, and this is just a 1, which of course means 2 pixels. And then you've got a 3 here, which means color 3. And so in this example here, you would be effectively writing 16 pixels of 0 to the screen. And in this case, which of course would be transparent actually, and in this case, you'd be writing 2 of color 3 here. The literal block, of course, works the same. You have a count of the number of pixels in that block, and then you have the literal nibbles. So this would be color 1, this would be color 2, and this would be color 3. And of course, you'd have loads more data here, but we're only showing very simple examples here. Now, as I say, I'm not imagining you'd probably want to be working with that unless you find a bug in my Echo Sprite editor, or unless you really don't want to use it and you don't want to use any of the other alternatives that can create this data for you automatically. But, you know, I like to try and explain the formats that we're using. So I've exported this sprite, and that's what we're going to be using today. Now, the code that actually executes the sprite drawing is using this common command called set hardware sprite. You'll see we're actually running it twice. So whenever we run this, it effectively calls the hardware to draw the sprite to the screen. So we're drawing the sprite to the screen twice. Once at 90,30 and once at 60,30. And so that's why they were say on the same Y line. But if I change this to 60,60 and run again, you can see we're now at different Y positions as well. So we have the potential here to draw the sprite in different locations, and we're specifying the RAM address of the sprite in memory here. And if I just find this, you can see we're loading in an RLE compressed sprite here. We've got some alternatives here. We've got this linear sprite, and we've also got a much bigger sprite here. So you can see that's my Chibico sprite. So this one was just done as raw bitmap data, but these ones are actual hardware sprites. So you can see that. Now, if we specify the linear one, we get horrible corruption. And the reason for that is that the code I'm looking at today is actually coded to only do RLE sprites. So we'll look at that in just a moment. And of course, it's this function that's doing the work. But the thing is that 0 page entries H and L point to the bitmap data, IXL and IYL point to the position on the screen. Now, before we can start using sprites, we do need to make sure our screen memory is set up correctly. So we define the visible location of the screen with these registers just here, but we would probably want to be writing sprites normally to a buffer somewhere. In this case, we're not. We're writing sprites to the visible screen. So of course that would flicker in a game, but it's just a test code. So that's not what we're doing. But in this case, we're defining C000 as our visible and our sprite working area for the screen. And then what we're doing is we're defining an offset. Now, if you think about it, you don't want 0, 0 to be the top left visible pixel of your screen, because what if you want your sprite to be half off the screen? So we're setting an offset of 8 pixels. So 8,8 is the top visible left of the screen, and 0, 0 would mean some of our sprite was off the screen. And then we've got some other settings here that are basically fixed that we just need to do to get the hardware into a working state. So we need to write F3 to this address here. We need to turn on the Sprite hardware here. And we need to enable the Sprite, the Suzy bus. The Suzy is the processor that does the sprites. So this is all just getting the Sprite hardware ready for us to work. Now this is the code that actually starts the sprite drawing, but there is also this data buffer here, which is what we have to pass to the sprite hardware to actually get the sprites drawing. And so what effectively we're doing is this is kind of a template, and then we're patching in the memory location of our sprite bitmap, then the X position and the Y position into these locations here. Now there's some other stuff. We'll go through all of this just very briefly and have a look at it. So what have we got here? So here we've got the color depth here. So we're using 4 bits per pixel here. Here we've got the what's known as the type. We just want to leave this as normal here. Now we've got various bits here. Again, most of this I think we probably just want to leave the same. Now you remember before, if we enabled that literal sprite and then compiled, we were getting nasty corruption here. But if we go to the sprite control settings here and SPR control 1 here, and we change this bit here to a 1, and we just compile again, you can see those literal sprites now work just fine. And so it's just a question of making sure that whatever our data is the same format as whatever we've got set in the sprite control block. You see the RLE data doesn't work correctly either. We need to go back into here and change this top bit here to a 0, and now it works fine again. Now if for some reason you were using combinations of data, you would want to set this, you know, in the same way as with these other ones, allow it to be modified. But as I say, this is just an example really. Here we've got some more options here. We probably just want to leave these the same. It's relating to the positioning of the sprite and things, but I think you just want to leave these. We're creating a sprite control block of just a single sprite here, and we're going to run it multiple times. It is possible to create a larger buffer with multiple sprites in it, and it would draw them all in one go. But I think that's going to make things overcomplicated. It's probably easier, unless you're really pushing the hardware to the limit, just to use a single one and run it multiple times. So we're just leaving that here. We've then got the memory pointer to our sprite in memory. The Suzy hardware accesses our normal memory. X and Y position as a word, you know, it's 16-bit. We've got a scale here, so we've got this set to 100 in hexadecimal, which is normal size. If I change these to 200 and run again, you can see these are now really big, and that's really the impressive thing about the Lynx hardware. It can do the Super Nintendo style scaling of things, and as I say, this is hardware scaling, so it's really fast, and that's quite a surprising thing about the hardware. So it's only a handheld system, but it had this really powerful sprite graphics. It's just a shame about the buggy documentation in some cases, but anyway, we can do those really nice scaling here. As I say, we've got this just set to 100. Again, you could modify this, make it more advanced. This set hardware sprite function we're looking at today, it's actually common for a variety of my systems, so I didn't want to have special functionality added to it for some systems and not others, at least where possible anyway. So that's why we're not using the scaling option. We've then got an ending here. We're again not going to use these. The hardware is capable of collision detection in theory, but again, I probably try and avoid using that. Just do it in software if you need that kind of thing. Now we've got a palette map here. You can see it looks very boring here. It's a 0, 1, 2, 3, 4, etc. So 1 nibble per color. Makes no sense to use anything else in 16 color mode, but if you were using 4 color mode, you need to define what those combinations of bits are going to actually be as a color within our palette. So this will become more important there to map those nibbles to the colors that we want them to actually appear on the screen. But as I say, this is correct for a 16 color sprite here. Okay, so that's our sprite control block, and this is what we're going to need to modify with our coordinates and then send to the hardware. So you can see here we're loading in the H and L address of our sprite, and then we're just writing these to this sprite source in here. So that's setting the data address of our sprite data. Then we're loading the X and Y position. We're just loading a single byte here. So it's a 16-bit entry, but we're only say loading a single byte. Now, if you were using some crazy offset, maybe that would be a problem for you, but with our offset of just 8, it's not a problem at all. We're then loading the sprite control block address, and we're storing this to FC10 and FC11. These define the address of the sprite control block for when we run Suzy. So now what we need to do is we need to actually start things. So there's a set of commands, and they're very fixed, to be honest. So we need to load these 2 bits with 1s here. This is defined as sprite start. This is known as the ever on detector. I have no idea what that means. I don't think it's documented what it means in the documentation, but setting it to 1 seems to work okay, so that's what I've done. And then we need to set the CPU to sleep. We can do that by writing a 0 to FD90. Suzy will then be able to take things over, and what we then do is we pause the CPU until Suzy has completed the job. And so Suzy will then go to the memory, read in the sprite, scale the sprite as required, write it into the bitmap memory at C000 onwards, and then return control back to us. So as soon as we get to here, the sprite's drawn to the screen, so there's no kind of delay or anything. That will just work fine. Now, for reasons I don't understand, the first bit here of the sprite control block is getting corrupted when we draw the sprite. I'll just show you. If I disable this here, you can see this second sprite now is completely trashed, and the reason for that, after much deducing, was this first byte here was corrupted. Now, I tried putting a debug monitoring tool in here, and it seems that it was this area here that was corrupting it. So I don't think it's a bug in my code corrupting it, and if it's something I'm missing, maybe I'm failing to correctly define the collision depository or something. I mean, it's perfectly possible, but I couldn't figure it out. So just to get things working, I've hard coded this in to write the correct data back here so that when you do a second sprite, it will work fine. But if I ever figure out what really is going on, then I'll fix the code. But anyway, as I say, as a basic example, this does work. And you know, if you're looking to learn a bit about the sprites and you just need an example that you can run, this will run just fine. Anyway, that's what we've got today. So as I say, please download AquaSprite Editor, and you know, it's open source, so if you want to improve it, go ahead and download today's source code. The bitmap data for the files we've run today is all going to be in the archive, so you know, you can run today's example and you can maybe have a play around and try and create a larger sprite control block that draws multiple sprites in one go. Now, if you really want to dig into things, you're probably going to have to download the official Lynx documentation. As I've said before, it's not great, but you kind of, you know, if you want to start playing around with quadrants and things, that's probably what you're going to have to do. But anyway, as I say, hopefully what I've given you today is enough to get you started. And you know, if you've got something that you know should work, you can then start to play around with something a bit more adventurous. Anyway, thanks for watching today, and goodbye. If you enjoyed today's lesson, please check out my website. We've got tutorials, source code and development tools for 6502, 68000 and Z80 systems, and a lot more systems coming in the future. We're going to be covering the 8086 and the ARM and a few other things as well going forwards. And if you've liked this lesson, if you've got questions, comments or suggestions on how it could be made better, please consider signing up to my forum. It's free, of course, and you can come along here and you can make suggestions, you can ask questions. And if you've got assembly projects you're working on, please let us know what they are. Maybe show off a few screenshots, tell us what things you've found interesting or what tricks you've come up with, because we'd love to know about it. Anyway, thanks for watching today, and goodbye.